Hello everyone, my name is Dennis Trujillo. I'm here today to talk to you a little bit about AI in radiology. Just to preface my background, so I have a PhD in material science engineering from the University of Connecticut. I've primarily been doing research related to AI applied to heterogeneous data sets previously, and here at WashU I support the HPC and also consult on AI workflows. So today I'm going to talk a little bit about multimodal AI and how it can be used to solve problems in healthcare. So just to give a preface to deep learning in healthcare. We know that there's a lot of promise with new emerging models to utilize deep learning methodologies to transform healthcare with advanced data analytics. So in terms of classification of disease or tumor segmentation based on different modalities that are available. So the applications span from imaging to enhancing personalized medicine with complex heterogeneous data. So up until recently, all of these data types have been used individually. So the promise of multimodal modeling is to utilize all of these or as many modalities in concert at the same time to generate a treatment plan recommendation or to do something with multiple data types. So the goal for this seminar is to connect deep learning technicalities with practical healthcare applications to inspire innovation and maybe get you guys on the pathway to investigating how you could use some of these models in your own practice in the future. So I'm just going to jump in with a technicality at the beginning. So I'm going to talk about the anatomy of a neural net. So a neural net is based on the idea of a human neuron or an animal neuron, where you have an input, a weight, and optimization and activation, and then those things are optimized with the loss function that are then mapped to an output layer. So the idea is a neural net can be a universal function approximator. Let's say you have any input and you have any output. You can create a map from input to output utilizing a very simple architecture. So the most important part, in my opinion, is going to be the activation function. That's where the nonlinearities come in. So in terms of the activation function, there's a couple of different activation functions that are used. There's the ReLU, the sigmoid and pan-H function. So these are just different functions that can map from one input that's been normalized to an output that's been normalized. So this introduces nonlinearity to this very simple architecture of input, weights, and outputs. So it's a very simple architecture that is then optimized using stochastic gradient descent, basically a minimization function to try and minimize the error from the loss function. The loss function is just basically like mean squared error, or it could be cross entropy for classification. But the main point is neural networks are fairly simple, but they allow us to do some very complex learning. So in terms of success stories, we know that imaging has been a success story within the domain of deep learning. So CNNs, convolutional neural nets, are crucial for medical imaging. They aid in feature identification and pattern recognition. So this has been used successfully for anomaly detection in radiology images and improving diagnostic precision. Some of the issues with any deep learning approach, though, have been in terms of the data sets that are used. So having a data set which captures the full distribution of future patients is very important. So it's very important to have a well-balanced data set. But in terms of convolutional neural nets, which have been the biggest success story, they're fairly simple in terms of architecture. So it's almost like taking an image and then looking for features within the image, utilizing a set of rules. So for example, a CNN can learn layer by layer how to see different features. So those features could be edges, lines, blocks. So it's ultimately a way of learning structure within an image. in a very common architecture is this ResNet 18 architecture, which is shown here. That can be applied to many new projects fairly easily. So like if you wanted to build something off the shelf with your own data, my go-to recommendation would probably almost always be to start with ResNet 18. So it's called ResNet 18 because there's 18 layers here, and it's a fairly shallow neural network. You can have networks that are very deep. The depth is represented by the number of layers, but the main point is this one is fairly shallow, which means that it can be generalized fairly well because it's learning a set number of features with each of those layers. So the more layers you have, the more complex features the network is going to learn. But with ResNet 18, it's a fairly shallow network. It can be applied generally to learn new information from any image-based data set. So it's good for classification tasks. You could also use it for regression as well if you change the output layer, but this is a very common model. So in terms of working with other modalities, image-based data is a very common modality. Textual data is another extremely common modality. So the best techniques for working with textual data are natural language processing. So NLP techniques are used for understanding complex clinical notes, medical records, and patient feedback. So you can take your EHR notes, you can take anything that's been transcribed from a radiology report and use that as an input to an NLP type model. So example use cases are extracting critical patient information, performing sentiment analysis on patient feedback, and summarizing vast amounts of medical literature. So the go-to success story of NLP that everybody knows right now is ChatGPT. The OpenAI models can be used for tasks like this, where you take an exported epic chart, for example, that might be something like 100 pages, and then you can summarize that over the course of a minute or two and receive the high-level feedback. So NLP is extremely useful for working with textual data sets. So we've talked about imaging, we've talked about text. Now let's talk about multimodal deep learning. So the idea of utilizing multiple types of data at the same time to learn something. So the idea with multimodal deep learning is to combine various data types such as images, text, and genomic data, and utilize all of these at the same time to gain richer insights. So this improves the accuracy with which you can do diagnostics because you have a more complete picture versus utilizing unimodal methods. So you can learn kind of like correlations, nonlinear correlations between different data types. So there may be something in the chart data that is also captured with the imaging data. So this is a way to learn nonlinear correlations within data. And the applications range from enhanced diagnosis to precision treatment and continuous patient monitoring. And just to give an idea for the architecture, or a general idea is you have all of these different image or all of these different modalities. You take all of these and you pre-process, you pass them to a model and you receive an output. This is more of an example of an ensemble-based model where you take a bunch of different learners that are very good at working with one subtype of data, and then you average them together. So in general, we know that there's multiple data types that everybody is working with. There's MR, there's CT, there's electronic health records, there's genomic information and wearable sensor data. So how can we combine all of this data and use it actually? So there's a couple of different methods. There's fusion models where you leverage data from multiple sources and at various stages you fuse it together. So it could be as simple as, let's say you have an image represented as a matrix, and then you append some textual information that's been rendered as an embedding, and you create a larger matrix. That is a very simple approach. An ensemble model is more like what we saw in the previous slide, where you have the best learners for each subtype of data, and then you average those together, kind of like in a voting or averaging type way, to mitigate the individual weakness of the various learners to create kind of like wisdom of the crowd or wisdom of the masses type approach. And then there's transformer models. These are what are emerging on the scene over the past few years as the most important type of model that's being used for every type of application. So they utilize a self-attention mechanism within a unified architecture to process and analyze data. They excel in handling complex relationships across large data sets and diverse data types. Okay, so let's talk a little bit about transformer models and how they work. So basically, we can use transformer models in healthcare with multimodal data. They can handle healthcare varied data types, improving upon RNNs and CNNs. They utilize a self-attention mechanism, which means that they can take basically an input and they can map it to an output with a series of weights or attention. So let's say that you have this phrase, how was your day? And then you have the same phrase in French, comment s'est passé ta journée? So this is learned with a series of weights called attention. So you have an attention mechanism and it learns the correlation between each of these words and how important or unimportant each portion is for the input versus output. So self-attention mechanisms allow for kind of mapping something that's textual to another textual output or something that's textual to an image-based output. It basically learns how important each component is input versus output. So it's a very versatile model, which makes it's showing a lot of promise for use as kind of like the universal model going forward. It's even being embedded on the silicon itself to make it more efficient in some cases.
Yeah, in fact, I think that's one of the reasons why it's such an interesting technology, right? Is that, I think ultimately you want really dense networks all the time, but they're extraordinarily expensive to do computationally. So up until recent advances in hardware-based acceleration and algorithms that helped with evaluating these models, they just weren't tenable. And so people came up with all sorts of machinations to make other lesser models work. And now they have these.
Yeah.
Extremely cool.
Yeah. These models are kind of a unified architecture. They can be somewhat complex to work with just because they work based on a number of parameters. So it's kind of a scaling law. You want more parameters to have a better model. And ultimately, you need more GPUs. But with embedding these on the silicon itself, you can have a much more efficient model, or you can do different tricks to make it to where these models perform better with less parameters. So what about ChatGPT? Everybody knows ChatGPT. Everybody's wondering, is this going to take over my job in the future? Something like that. So what is ChatGPT? It's actually a transformer-based model. GPT stands for Generative Pre-trained Transformer. And it's, I wouldn't call it a true multimodal model because it's working entirely with textual data. So it's structured in unstructured text from across the web, books, forums, etc. The idea with these types of NLP models has been more parameters, more power, and that typically means they're more expensive to run. So for inference, I believe there's something like 128 A100 GPUs that are used whenever you ask a question to ChatGPT. So it's using a huge amount of resources, and all of that is basically heat energy that is dissipated. So it's a very expensive model to run. It's not really scalable long-term. So it's you can see here what the scaling has been in terms of number of parameters versus time. So it's basically this is log scale and this is linear. So that means that this is exponential. So it's scaling exponentially and it's continuously growing. Right now, this is mostly textual based. to work with image-based data, they're using a variety of tricks. So if you play with the ChatGPT 4 with imaging data, they're not truly utilizing the transformer for the imaging data. They're applying different models and then extracting the metadata and then feeding that forward through the textual-based model. But the main point that I want to illustrate here is that these models are growing exponentially, and there's a huge energy cost associated with these, which means that there's actually considerations for, is the energy grid big enough to handle these models going forward? So this is going to be a huge power draw in the future, or even now. But it's a generalized way of providing textual answers because it's been trained on everything. It can give general answers about anything. But if you want an expert learner, you can actually make this an expert learner through a technique called RAG, Retrieval Augmented Generation. So with RAG, you can bring your own corpus. It's less complex than actually fine-tuning the model. The general architecture is here where you have your own documents. Those are then embedded and stored in a vector database. And those can be retrieved during query time and then fed forward to the large language model and then returned as an output. So all of this is doable with open source models or with OpenAI currently. So if you had like a textbook, for example, you could then pass that in and have a model which could answer questions from the textbook. Or if you had a patient chart, you could pass in the patient chart and then ask questions about the patient chart and get accurate answers. So RAG is a very powerful technique, but there's issues in terms of like, if you're running your own service, then you need to have the compute for it. If you're using something like OpenAI, then you need to anonymize patient data if you wanted to do something like that. So there's various considerations around this. So this is where we truly get into multimodal image-based solutions. So there's a type of, so anytime you work with a transformer-based model, you have to create something that's called an embedding. So with text, what that means is you take a string and you convert that into a vector. So you convert that into a numerical representation of the string of words. With images, you can do the same thing. So there's a type of vector embedding called CLIP, which stands for Contrastive Language Image Pre-training. So this model can allow you to create an embedding from an image, and then that allows you to bridge the gap between visual and textual data, facilitating multimodal learning. So now you can take a string of words and you can take an image and you can associate them. So you could take almost like a radiology report, and you can take the image, you can associate those two things, and you can have a way to say, via a multimodal model, show me all images with tumors over 2 centimeters in diameter in the left, or I'm not an expert in medical terminology, so left versus right versus whatever. So you could ask for specific things now, utilizing a vector embedding of an image along with a vector embedding of text. So it understands and aligns the context of images with natural language, enabling more intuitive search and classification tasks in healthcare. This can be used to improve medical image analysis by correlating diagnostic images with clinical reports, or vice versa. You could correlate it with genomic data. Perhaps there's a structural information in the tumor that is similar for different genomic mutations like HER2 versus BRCA1 versus BRCA2, XYZ. So it's a very powerful technique. So here you can see the general architecture where you have a label for this image. So Pepper the Aussie pup. You take that, you encode the text, you pass that as an embedding, and you do the same thing for the image, and you cross-correlate these things so that the model can then learn those correlations. So this is another very powerful model, MedSam. So this is via a paper that came out at the end of January. There was a segment anything model which was released by Facebook or Meta, which basically allowed for segmenting anything from any image. So you could find a horse in a picture of horses in the woods or something. But now people have taken that model and they've fine-tuned it for medical applications, hence MedSam. So MedSam introduces a universal approach to medical image segmentation across modalities and diseases. Ron was talking about MDAI earlier. So this is one of the models that's supported through different architectures. This is the state of the art in terms of segmentation. And it works with different modalities. It's been trained primarily with MR data, although it has been trained with endoscopy data as well. So you could use this almost as a universal model for segmenting things based on a few inputs. So you could use bounding boxes, or you could just annotate with a few clicks and have it auto segment. So it's a very powerful model. So this was trained with a very large data set. This is something that you can now take, fine tune very simply and use for your own applications. So the best way of working with any deep learning model is to find a foundation model, something which solves the general idea of what you want to work with, and then fine tune it for your own purpose. You don't want to reinvent the wheel. The idea is find the best model for your purpose, fine tune it, and then use it in that case. This is looking to be the universal or foundation model for segmentation at the moment. So this improves the experience of annotating data. This could be very useful, like in the reading room, for example. So it's a very powerful model. So it supports 3 types of prompts: the bounding box, segmenting via a set of points, or via text. So the text isn't available yet, but I assume that will be released fairly soon. So you could say segment the spleen in this image, or segment tumors greater than 2 centimeters in the left side of the image, for example. So it's a very powerful model. So there's a question like, how can we utilize all of the amazing data that we have at these different institutions to actually train models? The solution for that is federated learning. So federated learning enables decentralization of model training across devices or different servers without sharing sensitive data, enhancing privacy and security while complying with data protection regulations. So the main idea here is you have a global model and you have local models. So let's say, like on your iPhone, you have all of this fitness information, and you want to have a model that will predict how fast you'll run your next 5K. So there's a global model that lives somewhere, and there's a local model that lives on your phone. So what you can do is you can fine tune those local models and then send the weights to the global model in a way that would be anonymized to where you have an improved local model for your own device, and you improve the global model as well. So federated learning allows for working with multimodal data for collaborative development of AI tools that analyze complex healthcare data across institutions. Some of the key applications could be personalized medicine, disease prediction and prevention, remote monitoring and diagnosis. And it's a great technique, but there are some
challenging.
Yeah.
And it's yes. Anyway,
yeah.
right.
So some of the challenges include data heterogeneity, data complexity or model complexity, communications overhead, and the need for privacy. So there's different ways of doing it. You can take the model weights, but there's ways to reverse engineer from the model weights the data. So you have to be very tricky with the way you process your data. Anonymization is key at the earliest stages. So it's a very powerful technique, but it needs to be improved on and simplified.
I'd say it's one of those things that's not quite ready for prime time. This is one of the things we worked on. So I recently came from Hewlett Packard Enterprise, and we used to put out all sorts of these kinds of models for global customers. One of the big problems with them is, well, reverse engineering. That's a really big problem, because you send your weights actually are your data in a lot of ways. But the models themselves suffer. I've never seen a federated model that performed well, and they also are prone to kind of spinning out of control. As you can imagine, you get a lot of like heterogeneous data inputs, but the model doesn't know how to average all those together. I mean, it just says, well, this one's probably just as good as this one, but they might be getting very different data. So now you're starting to average all the weights together in some arbitrary format, and there's really no way for the model to necessarily converge in that case.
Yeah.
But yeah.
So probably something that can be improved on, but there's still a lot of promise in the general idea of having local data, sharing some information in terms of a local model weight to a global model, and having improved local and global models for everybody. But in terms of emerging trends for what's coming on the scene, I would say that smaller open source models running on private devices are going to be the future. So everybody is playing with ChatGPT. Very soon, people are going to have something as powerful living on their phones, a private large language model that you could share your own data with. It would not have to leave the device. So smaller models running on private devices, I would say that's probably going to be a thing with Apple, even at their next WWDC. So yeah, there's a lot that is coming on the scene. There's been optimization, specifically from the Apple side, for working with the M1 and M2 chips. So Llama 2 is an example of an open source model that they've optimized to make extremely fast. They're optimizing so many different things day to day. Like if you follow this on Twitter or X, you can see like every day there's a new set of models that are being optimized for reinforcement learning or for large language models. So pretty soon you'll have something as powerful as ChatGPT on your watch, on your phone, being able to give you specific answers about your own data without it having to go to the cloud. So that's very powerful. There's also different architectures that are showing up. So there's SSM, state space models. These are great because they're much more efficient and they're ideal for real-time applications on edge devices. And then there's different techniques like model compression, like pruning. So basically taking your models, simplifying them by removing redundant weights to make them as small as possible, but still give the good results. There's also lightweight transformer models and the ability to actually create silicon, which emulates the transformer model. So they're almost etching these things on silicon to make them as efficient as possible. So fairly soon, I would say you'll have extremely powerful models on device that can work at the edge. So you could have something in the hospital room that is working with live data without it having to go to the cloud to give some type of insights. So something maybe even running on the endoscope, something running on the monitors to be able to do amazing AI. So yeah, I would say there's a lot of amazing stuff coming in the near future. It's evolving extremely quickly. And federated learning is one of those techniques that I'm looking forward to as well for improving global models and allowing for sharing data without exposing patient information. So there's a lot going on. We're trying to build a way for people to share research data back and forth, like papers or just talk about AI. So we have a Slack channel. If you want to join, it's this QR code on the left. And then if you want to learn more about the RCIF and our compute capabilities, that's the QR code on the right. So we're bringing online some H100 GPUs. There's basically, these are almost a golden commodity. I've heard of startups getting loans against their H100s. So it's almost something that, well, it is actually export controlled. So like these things aren't being sold to China, for example. These are extremely valuable resources, and we're bringing some H100s online. Scott could talk a lot about those.
Yeah.
So I guess that leads
Exciting.
nicely into like a philosophical question I have with this whole system, which is with the increased commoditization of the models themselves, and as we get more and more sophisticated with the hardware acceleration, we're essentially centralizing the amount of players that have the ability to make these things.
Exactly.
So if we build these systems and we keep getting better and better at them, they're gonna keep getting more and more expensive in terms of the hardware itself. So is it actually feasible for every device to be able to run the most sophisticated local models on device? Or are we gonna have to deal with this bear of like, we may end up at a point where like Meta and Google and Amazon and Apple have they're the only ones that have the ability to run the most sophisticated models, and everyone has to deal with like the data privacy situation where,
I think that there are two sides to this, right? So one is that, I think one of the things that we didn't really cover here was that there are always two sides to AI. One is the training, okay? And then the other one is going to be the inference. And I think the inference side of the equation is kind of what you're talking about. But the training is also important because the training gives you the weights that you will eventually use in whatever inference model you use. Inference models are typically a lot cheaper to run. And I think Dennis was talking a little bit about that on one of his 5 points at the end. He was talking about these techniques like distillation, quantization, that really take these very large and extremely complicated models with very complicated weights and squish them down into usable forms. Those can be leveraged pretty effectively. The problem is that they always need to be retrained, right? They always need to have continuous updates so that they don't spiral out of control. And that's kind of where it feeds back into the training loop. Right now, if you are so I came from Hewlett Packard. We made lots of big equipment. We also had a lot of these kinds of solutions out there, but places like Hewlett Packard could not get H100s. I was talking with people at SC23 just a couple of months ago. They were saying that their large data centers did not get their allocation from NVIDIA because NVIDIA is only selling them to the hyperscalers. And so your Amazons and your Microsofts and your Metas, they're the ones getting the hardware, and the hardware honestly is the key. I think as you saw, like what Dennis was talking about, these are not complicated things. Like theoretically, very simple. We've had these numerical techniques around forever, and these are some of the simplest ones. It's like so I was a computational physicist, and so we had this simulation technique called forward Euler. The simplest thing you'd ever learn in your classes. That's essentially what this is, except they've added in some nonlinear units and stochastic gradient descent. Those are the two kind of like special ingredients. So those are not the hard part. The really hard part was the hardware. These things could have been possible in the 70s, but we didn't have the hardware, but now they do. And so really, that's where it all kind of funnels down to. One of the cool things about this institution is that they made a commitment to buy this hardware. And so we now have this sitting in our data center. So if you want to do projects like this is kind of a magical time. You have access to the data because we have a ton of data here. Got access to the hardware. All we need is really access to the researchers who have the creativity to come up with the applications to put onto these things. And then, we can get some great papers out of this and get those models onto devices and start doing that cycle. Now, the people like Meta and Meta and Microsoft and Google Cloud Services, they really want these kinds of applications too, because they can offer them as a service. So, they may have control, but they also don't have you all either, because that knowledge and the data gets distilled from somewhere. So there is a place for all of us in that ecosystem, I think. But, who knows? Maybe they'll just buy all of us and then not have a place anymore.
Yeah, data is definitely a very important thing, having access to unique data sets. But then also I would say that the open source community is making big leaps. So as soon as the GPT models became a big thing, Stanford started releasing Llama. So there's a big push from the open source side to make models that are nearly as good and much smaller. So there's a lot going on all over the world. I mean, this is such an amazing technology that there's a lot of pressure to create amazing models. So this is almost like a matter of national security to a lot of nations to have very good models.
Yeah, and I think that also kind of points that these tools are there. We can get them, just download them, put them on our machines, or whatever machines you can get access to. And you can train your models, and there are tons of recipes that we can use. I think Dennis was just showing a few of the recipes of how to put this together, but you all have ideas. There are
So
ways
if
of
we,
putting it together.
if we have specific applications that we're like thinking about or
Mm-hmm.
currently in development on, and we would like to like consult with you guys, show you what we're doing, see if you have comments. How would do we just email you?
Yeah, absolutely. Actually,
Or
the
do we do
Slack
that?
channel is a great place
Yeah.
to go as well. Dennis, so on our page, I think it's like docs.chpc.wusl.edu. We have a number of ways of contacting us. You have a Calendly link that you keep up like all the time. So anytime you want to get a meeting with Dennis, he's pretty available. Personally, I'm always in my office. So if you come by East Imaging, stop in.
Are you on the third one?
Yeah,
Oh, okay.
yeah. So I'm in 338. So kind of near
We're on the
Canada.
second.
Yeah. Probably right.
Yeah.
I don't know. Sorry, I started in June, so I'm still kind of getting used to the hospital.
I feel like you have a user through Canva, don't you?
Yeah.
Because this is like to be purchased by individual PIs, is that correct?
Which?
Like user and a certain number of users for the server, because I used to have one through my former PI. So this is not like, most of the people here are T32, like research residents, being paid by the government to work for the hospital. So we're not like being paid by WashU or in any form financially related to WashU. I mean, let me keep a computer, but that's different. So I feel like this is exactly, you guys still have like certain number of you have users through Tammy purchasing
Right.
those users for you guys, right?
I mean, I'm not exactly sure. I know there was a
Yeah,
lot of
different-
restructuring, but
Yeah, I feel like you guys.
yeah.
That's all here, and you're, yeah.
You know what? This is a really great comment because.
I mean,
this
I've
confused-
certainly lost my access.
Yeah.
Yeah, so.
Well, this really confused me a lot when I first got here because I didn't realize there are two IT infrastructures for MIR.
It's very
I
complicated.
didn't even notice until about a month ago that there was like another like whole clinical group that was doing their own work and had their own deployments. We're not related to OneRat. So
Yeah.
we operate independently. We're a shared resource and we actually have like free access to some of our resources. So if you just want to get an account and do stuff, feel free. Otherwise.
Correct me if I'm
go.
wrong, but the T32 residents are temporarily funded through WashU because the grant is through.
Switch from
You switch,
DJ to
okay.
WashU. And like
Yeah.
another thing to point out there too, for all you guys, it's like, obviously with the RCIF, also preparing with any PI, clinical PI or faculty, is we can apply for pilot funds. That gives you dedicated time, and that can be done every year for different projects. And we also through the, residency, we have other funds we can access, so I would say if that was ever a question, we could always address that, but I'm pretty sure, isn't there a tiered system?
Yeah, there is. So even without any funds whatsoever, you can still access some of our resources. But on our pages, which are at docs.chpc.wusl.edu, we have a list of how to get funding as well and where you can apply for it. And then we have like tiered access. If you have a PI that you want to work with,
Yeah.
oftentimes they will have
Yeah.
access and you can get access to them and we're happy to do that as well. Yeah.
Anything, if you want to use it, I would say email us, and we can help navigate all of
Yeah.
those questions. But yeah.
Yeah, I feel like I need to email you and you can navigate. my
I
place.
was just like,
Yeah.
being like this, it all comes down to access to the servers.
Yeah.
So-
And I'm pretty sure that we can make it happen. If you
Yeah,
have
I mean,
ideas that you wanna
PIs
have-
are, I guess PIs are shared, they're paid by WashU, but work with us, so those are the links to.
I think our PIs are also NIH funded, so I don't know, we're big through from NIH, but through Washington.
No, yeah. All of that.
I feel like it's-
So I guess the other thing, just thinking about this holistically, guys, we have 3 more sessions. I know quite a few of you are working in the space art projects. Is there any topics or questions or anything that you have for Dennis or Scott or even operationals, like think about anything with projects or things you would want to hear about. Because we have the opportunity to kind of customize the next few sessions. I know we kind of prescribed what we were gonna go over, but I want to make sure that if there's questions you have, that we have the opportunity to, address it, dig in the weeds on it. So I'd say if you have them now, like, cool, we'd love to hear what those topics are. But if not, like, please email me and we'll kind of funnel all that in.
I have a question. I don't know if it's a short question or it will require like a public discussion. Are there some application that I can use these tools without necessarily needing to trust the output? Kind of a helper,
Like as a thinking tool? Or,
as a research tool,
Mhm.
but without it be the main kind of, like maybe in conjunction with other tools like traditional tools, and there would be like some other way to compare or to add more significance, I guess.
Yeah.
I don't know if it's.
yeah, I mean, like, these things don't have to be used, as like the one total solution. You can imagine that they might be a component,
It could just be an aspect of your
Yeah.
clinical decision making, like, let's say
Yeah.
let's say you're reading like an auto-aligned scout and you're doing the reading yourself. But there's also an AI algorithm saying, hey, there might be something anomalous here that you should pay more
Mhm.
attention to. And then that would allow you to say, okay, hey, maybe I should pay more attention to this particular scan, but it doesn't necessarily mean that you will find something that you feel.
So I guess to apply this to research, you would do both and then see how much did this help this group or like this.
Yeah, right.
Okay, that's one good application.
So I think I have a question. So there's like one aspect of it that's like, how far can we push the models with like as much data as possible, right? But in a research setting, a lot more often what we run into is we are on the cutting edge. Like, let's say we're developing a brand new tracer that is looking at something that maybe no one else has looked at before, like reactive oxygen species in the brain, like presence of free reactive. I mean, people have looked at that, but anyway, there's not a reliable tracer for it, right? So let's say we're looking at that and we maybe have scanned 30 people, right? And we need to do segmentation, or we need to do some type of region of interest analysis. So it's more of this aspect of like, we don't have that much data with this specific thing
Mhm.
because it's on the cutting edge. But we would like to know how to best utilize some models that have information coming from other places and then add onto it this cutting edge aspect that we're looking at. That's like, I think the big question that I run into all the time is like, I don't have enough data for a lot of these huge models, or to even like augment a lot of these huge models. But I do want to leverage like somehow.
Yeah. It's always complicated, right? Because too little data is the bane of a lot of these like really large kinds of, and plus they're a bit of a black box. Explainability is still a very active topic in like kind of deep learning research. But there are also a lot of other kind of traditional machine learning algorithms that I think do really well, and they're very rigorous mathematically. So you kind of know what are the error bounds that are coming out of this for like small data sets. It gives you a very kind of rigorous concept. You, as a researcher or a clinician, can have more confidence in what that's telling you, as opposed to having to take kind of what the black box gives you.
Yeah, so like with imaging models like Resonate 18, you can take that as a pre-trained model, load the weights from that were used from learning what a cat versus a dog versus whatever is. And because it's a shallow model, it would have learned just like simple things like edges. So you can take a model like this with a small amount of data because all it's learned is edges, and you can fine tune it to work with whatever type of data. So like, let's say you have 200 imaging examples. You could probably take those 200 images working with a pre-trained Resonate 18 and still get decent answers. So it is possible to take off-the-shelf foundational models that have been pre-trained and use them for research applications. And I think if there's interest, I could probably like over one of the next sessions give a demo on how that can be done. and talk a little bit about explainability within imaging models.
Is there a way to estimate how much data you need for a certain application before you start using it?
I would say that you're probably working with, if you're working with a pre-trained model, I would say that on the order of hundreds of data points would be the minimum. And I would say that it's very important that you have a diverse set of data that represents the distribution that you'll see in the world. Like, for example, if you train, if you want to build a classifier for training dermatology related lesions, and you only show it like one or two types of lesions, and you tell it to try and classify a third type of lesion that it wasn't shown, it's not going to work, obviously. So having a good distribution of data and a minimum of hundreds of data points, that would be possible.
So question about data. So, you know, obviously, BJ, this campus, we produce a crap ton of imaging data every day. And that's over time. And thinking that the cleanest clinical data that goes along with that would be since post-Epic, you know, how many years ago that was. Have you guys, just think about the more data, the better, right? And if you can pull data sets, like one question I had is like, how accurate, if we do natural language processing to pull the data, are those the clinical applications we're actually looking for? But the other question I have is, have you guys gone down the path of, you know, BJC, like enterprise-wide point images?
So we have a proof of concept. I mean, Dan Marcus, I'm sure you've had several conversations with him. So we did a poll not too long ago of like Tammy specifically wanted to look at a bunch of Autoline Scout images. So we pulled like 5,000 Autoline Scout images from all across the BJC database through Mirror.
Yeah, so
I mean, it's great because you get the data that you want. In the current iteration, it takes more time than you would like it to, and it's more resource intensive. Like we paid for those images quite a bit.
I've done a
So
similar thing in the past, like during like COVID, like we pulled
yeah,
every close section we've done through all of the BJC to look at a certain project for Toy Society, but it's just more of a, have you guys, I'm more thinking pipeline of capabilities, process, you know, all those different things. Have you guys really thought about that or worked through it?
Worked through it. We've thought about it a lot. Now, worked through it, that's a loaded term. Yeah, I mean, in a way, that's kind of the philosophy of what, you know, Dan wanted to do with Mirror was essentially prospectively pull data sets that people would want to use into a usable location. So right now, you know, just to get into a little bit of the weeds, we have a number of different storage systems. Most of the data is stored in BJC and giant databases. You know, there's a data lake out there as well. That's not great if you want to put it next to Silicon and do processing. So we have another very high-speed, large volume, 18 petabyte system that's co-located with our high-performance computers. That's where Mirror has been pulling data. So it's essentially 24/7 trying to pull things out of the packs that we think people will use for research, put them into this like very high throughput storage so that when people come to us, want to do processing on it, they'll have it. Are we doing a good job? I don't know. I mean, part of that is the feedback loop. You know, like we need people that say, yeah, this was great. This was exactly what I wanted. Or, you know, no one cares about that stuff. So, you know, part of it is that piece is missing. People have ideas. Again, you know, we're the people who talk to.
How is the mirror data, I guess, query? How do you query it? Is it any metadata associated with it? Any like report?
Yeah, see, it depends. It really depends on the poll that people are doing. You know, I know that all of the radiology scans that are done within research automatically go in Mirror. Those come with all the DICOM headers. Some of, yeah, I don't want to misspeak. I can probably point you for some of the PACS polls. I know that they've been wanting to pull a lot more than just the DICOM headers out of it, right? And you know, including like health record information as well. I don't know if they've actually done any of that.
I was gonna say, as of like a year ago, because we wanted to filter by what was in the RAD reads, and as of a year ago, there wasn't that ability yet.
Yeah,
I don't know if it's changed.
Yeah, I need to talk with Jenny about that. She would definitely know. But yeah, definitely on the, if it hasn't happened yet, I know that there's a lot of interest in that happening. Because that's, again, kind of avails you of, these kinds of techniques that you can do multimodal, inference. So,
Yeah, I think it's a somewhat complex thing with multiple steps at this point, and I think there's always some level of bureaucracy and resources that kind of shape how this exists. So yeah, I think it can definitely be improved on. But yeah, I mean, if you guys have ideas for projects, we're happy to help facilitate those as much as possible. I mean, our main day jobs are as HPC engineers. So like whatever time that we have available outside of that, like we're dedicated to helping you do your best research. So feel free to ping us. We'll make time. We'll do everything we can to make it happen.
yeah, we can also direct where other resources go. So if there's data that you need, maybe we can get, that prioritized in here. Because that's feedback that we need.
Well, we're at the top of the hour.
Awesome.
Thanks, guys. It was a great session.
Thank you very much, everybody.
Yeah, I think it's gonna be better with flywheel discovery too. I know we finally have that deployed.
I don't know anything.
I agree. I just,